Well, here we are again. We begin the semester with a bunch of conversion factor problems, and it looks like we're going to end the semester with a bunch of conversion factor problems. We're not going to have time in class to devote as much attention as we should to some of the conversion factor type problems in chapter 13, so I thought I'd do one of these handy dandy little videos and work through one of the end of chapter problems that is very closely related to one of the mastering chemistry problems, and you're going to certainly see some variations of these on the final. So the one I selected to take a look at is problem 13-48. Okay, it is one of those classic chemistry conversion factor solution concentration questions. And as you're well aware now, we have boatloads of solution concentration units, and a very common question is, here's some parameters for the solution. What is its molarity, its mass percent, its whatever the heck else they can come up with. And so it's a very common question, and it's not difficult, but you do have to be really careful. So, as we often do, let's take a quick glance at the question itself, and then let's tackle this thing. Now, I'm going to keep track of some of the vital information and answers and stuff along the side here. And we are dealing with vitamin C, and they give us its formula, C6H8O6. And it's going to be really useful to know its molecular weight, 176 grams per mole. And this is the solute. And we are told that this stuff is dissolved in water. So H2O is the solvent. Finally, they give us very specific bits of information about how much vitamin C and how much water together make up the solution. And the amounts that they give us are 80.5 grams of the vitamin C. We have 210 grams of water that this vitamin C is dissolved in. They gave us another bit of information that will be useful at some point in the future, and that is the density of this solution. They tell us it's 1.22 grams per milliliter. Now, I'm going to modify that number in just a moment. I've been talking since almost the very beginning of the course. When we are doing conversion factors and other type calculations, you always, with your numbers, write down the unit and very often write down what it is. It's not grams, it's grams of carbon dioxide or something. I can tell you right now that is never more important than when you're doing these calculations, because every one of these calculations involves something about the solvent or the solute or the solution. And if you are not careful, you're going to end up with lots of numbers with units of grams and moles all over the place. And you are going to need very specifically grams of solvent, and you'll just have a bunch of numbers with G next to them, and you won't know exactly which one is solvent or which one is solute or which one is solution. So it is vital that you keep those very carefully noted. For example, the density they've handed us, the 1.22 grams per milliliter. Now, they tell us the density of the solution has this value. I'm going to write it out, and you'll see why as we move along here, because this will, I think, be very helpful to a lot of students as they tackle this stuff. What this is 1.22 grams of solution per 1 milliliter of solution. Okay? In other words, these numbers are not vitamin C itself, the solute. They are not H2O, the solvent by itself. They are related to the solution, the combination of the vitamin C solute in the water solvent. So it's vital that we make note of that and keep this stuff in mind and be very careful as we do these calculations. So off we go. The first part of this, and yeah, I'm going to write right in front of my face because you know what the hell. The first part of this they want us to get is a mass percent. What is the mass percentage of this solution? That's what they're after. And so we have to remember our definitions of all the different solution concentration units that we encounter. A mass percentage is simply the mass fraction times 100%. And so I'm going to need, in order to make this one work, the number of grams of solute over the grams of the solution, the total number of grams. Remember, that is mass fraction times 100 makes it mass percentage, which is what this problem is asking for. Now, I look at the information the problem presents me, and I see gram solute. I have 80.5 grams solute. That's pretty simple. I'll simply write it down. 80.5 grams. And you will notice here I am, C6H8O6. I'm going to write that a lot. It's going to be a pain. You're going to go, do it, because you're going to have a lot of numbers. I'm going to have the convenience of being able to erase a lot of the numbers here and keep going on the board, but you're going to have, you know, a piece of paper in front of you with numbers all over the place, and you have to keep careful track of the numbers that are, you know, solute related, solvent related, solution related. So do be careful here. Now, it happens right there. Grams of solution. They didn't give it to us, but it's not hard to see where this is going to come from. I have 80.5 grams solute. I have 210 grams of solvent. And so yes, 80.5 grams solute, C6H8O6, plus 210 grams solvent, H2O. That is how I'm going to do my calculation, times 100. That's going to give me my percentage. And if I then just take that and get out the handy dandy calculator and punch that through, I'm going to come up with 27.7%. Okay, the solution is a little over 1/4 vitamin C by mass. So it's a pretty highly concentrated solution of this stuff. And so there it is, the mass percent. I'm going to keep track of these as we go along. Part A, the mass percent of this is the 27.7%. I'm also going to keep, you know, it's also a good idea to keep track of some of the other numbers here. Like, for example, this thing is, you know, 290.5 grams solution, okay? And that number is going to be useful at some time or another. When you're doing these calculations, you know, certainly you can, you know, use the results of one calculation to help you with another without having to, you know, go back and recalculate, you know, some part of this problem once again. So that's a pretty straightforward one. So what I'm going to do is then, you know, keep track of it here, or erase this section, and we'll move on to the next one. There. Now the next part, part B. If we thought the mass percentage was fun, now we have mole fraction. Oh yes. Now we've seen mole fraction before. It comes up when we talk about partial pressures in the gas law chapter, but it's back because it is another way of expressing concentration. Now, the definition of mole fraction, this is one you just kind of have to remember, and we've seen it before. Moles solute divided by total number of moles, which would be moles solute plus moles solvent. Okay. Now, if they wanted mole percentage, you would multiply by 100 and stuff. This one just says give us the mole fraction. So that's the calculation. these are the bits of information I have. And yeah, it's pretty straightforward to see that we are going to be turning the number of grams of vitamin C into moles, the number of grams of water into moles. You know, ooh, big surprise there. And so off we go. 80.5 grams of C6H8O6. I already know its molecular weight, 176 grams per mole for C6H8O6. Moles, C6H8O6. I'll be able to set that to music sometime. All right, so I punch that out on my handy dandy little calculator, and I get 0.457 moles of vitamin C. Okay, that's pretty straightforward. 210 grams water, the solvent. 18 grams is 1 mole of H2O. And that gets me, and oh, what was it? 11.67 moles of H2O. And I look up here and I see I don't need on the denominator moles of solute and moles of solvent. I need them both. So I've got to add these together. Total number of moles. And we just punch that out in the calculator. We get 12.12 moles total. Okay? Or moles of solution. Okay? And so we punch, put those numbers together and punch it out on the calculator. 0.457 moles. Oh, one more time. C6H8O6 over total number of moles in the solution, 12.12 moles solution. And we do that, punch, punch, punch. And what did we come out with? There it is, 0.0377. Okay. So almost 4 out of every 100 molecules in here, number of moles, is actually a solute molecule of vitamin C. The remaining 96 molecules are the solvent. Okay, it's quite a bit different to look at it in terms of number of particles versus mass of the various particles. But I am going to write some of these numbers down because we are going to need them. That this is the mole fraction. I'll need 2 of those there. 0.0377, and this is 0.457 moles, C6H8O6, and 11.67 moles, H2O. Okay, those might be useful in the future. So I can keep a list of these things here. And let's see. Oh, I know. Let's clear some space, and let's move on to part C. And as I was having a good time erasing that spot there, I did remember I wanted to make mention. Remember, mole fraction has technically no units on it. It's simply calculated as moles over moles, the moles cancel, and so 0.0377 is the mole fraction. There is no other unit that gets attached to that. So part C. Okay. Part C of this problem. Now they want the molality. Okay. The molality, oh, that's one of those mysterious little concentration units. This one, again, it's, you just need to have the definitions of these things, kind of filed away up there someplace. This one is defined as moles solute per kilogram solvent. Okay, that's its definition. And again, keeping careful track, solute, solvent, solution, and so forth. This one is solute and solvent. Now, we have all the numbers necessary to work with this here. In part B, we calculated the moles of solute, and it's the same problem, still the same number of moles, 0.457 moles C6H8O6. Kilograms solvent. Now, they tell us it's 210 grams of solvent. If this were chapter 1, we'd go through that calculation, but my gosh, we're veterans of this nonsense now. 0.210 kilograms H2O, the solvent. And so that's the calculation, nothing too terribly fancy. We take that one, punch it out on our handy dandy little calculator, and what should come out is 2.18, and the unit is molal, okay? Symbolized by an italicized M. I'm lucky it looks like an M at all, so I just make an M with an underline to indicate italicized M, because that's different from molarity, the next one, moles per liter, which is a big capital M. So there's part C, pretty straightforward. We'll keep track of that one as well. 2.18 molal. Okay, so one more time, get that space cleared out and on to the next part. Part D, molarity. Now, of all the different concentration units in chemistry, this is our favorite. Symbolized by a big fat capital letter M, its definition, moles. Now we say moles per liter very often, be careful. It is moles solute per liter solution. Okay, so moles per liter. So we need moles of solute. Already had that way back in part B. We need liters of solution. And here is where we run into a bit of difficulty, because what they've handed us in this problem is grams of solute, turning that to moles, we already did that. We had kilograms and kilograms of solvent, and that's it, except for the density. That's why a density is here. The density is necessary in order to deal with molarity, because it's the only one of these concentration units that actually has a volume rather than a mass or a number of moles in it. And so before we can make this work, we need to turn the mass, not of vitamin C, not the mass of water, the mass of the solution. Notice how we knew that. We kept track of all that. And so we actually noted that this solution was 290.5 grams of solution. That was all the way back in part A. And so here's where the density is going to play a role and get me 1.22 grams of solution is 1 milliliter of solution. Okay. And if I punch that out on my calculator, if I punch that out on my calculator, I'm going to get 238.1 milliliters of solution, okay? Which, again, in chapter 1, we would have gone through the, milliliters to liters, but, heck, we're experts at that by now. 0.2381 liters of solution. There. Now I have all the parts necessary to do the molarity calculation. And so away we go again. Moles, there you are, 0.457 moles C6H8O6 over liters solution, 0.2381 liters. And yes, on the calculator, and out comes, what is it, 1.92. Molarity. Part D, 1.92 molar. Okay, so there's the molarity calculation. So there's the answer to all 4 of these. Pretty straightforward. You do need to remember your basic definitions, and then just be very careful between your solute, the solvent, solution. Make sure you write down all of that stuff on every one of these calculations. Now, this problem that we're looking at ends here, but I'm going to add one more bonus point because, after all, who doesn't want to keep doing one of these calculations? And that is one of the colligative property questions. Question, what's the freezing point of this solution? So let me clear some space and we'll add that bonus in as well. All right, the bonus. Okay, for the bonus, I just simply wanted to tack on something we've already done in lab, but it follows directly from these types of calculations here in chapter 13, and that is, what is the freezing point of this particular solution? Now, recall that the cute little freezing point calculation is the freezing point depression, how far the freezing point will go down. As you remember, when you put anything into water, you're going to push that freezing point to a lower temperature. Is simply related to the freezing point constant for water, Kf, and we'll give you the value in just a moment, times the concentration of the solute in there, and this time it's expressed in molality. And so for water, the constant is 1.86 degrees C per molal. Our particular solution, looking at the molality, there it is, 2.18, the answer to part C, 2.18 molal, okay? And so, very simple calculation, you know, punch that out, and I came out with 4.01 degrees C. And so, now remember, that doesn't mean the freezing point of the solution is 4 degrees. You can bet that's an answer choice on the final, so be careful here. This is the freezing point depression. The actual freezing point of this solution, therefore, is the normal freezing point of the solvent, water, in this case, 0 degrees, minus the freezing point depression. And so this solution is going to freeze 4.01 degrees below its normal freezing point, 4 below, okay? Which is pretty cold, but, you know, not too bad. And so there, that's a quick little reminder of these freezing point type calculations that, you know, go hand in hand, quite frankly, in chapter 13 with all the concentration business here. So together, concentrations, know your basic definitions, keep straight the solvent, solute, solution, and practice a few, and you'll be fine. See you later.